November 3, 1942, Vancouver, Washington. The keel plate for a ship designated MC Hull 1092 drops into position on Building Way No. 3 at the Kaiser Shipbuilding Company's newest yard on the Columbia River. Within 72 hours, workers will bolt together, weld, and launch an entire aircraft carrier, not a cargo ship, not a barge. A 511-foot warship capable of launching 28 combat aircraft into battle against the Imperial Japanese Navy. Traditional naval doctrine said building an aircraft carrier required 18 to 24 months of careful construction by master shipwrights. The Essex-class fleet carriers America was rushing into production took 20 months each, and that represented a manufacturing miracle that had naval planners celebrating. Henry Kaiser proposed something that naval authorities declared flatly impossible. He would deliver 50 escort carriers in less than 2 years, using welding techniques and assembly line methods borrowed from automobile factories. The admirals laughed him out of their offices. Kaiser went directly to President Roosevelt. The problem wasn't just visible on maps of the Pacific. It was mathematical, brutal, and getting worse by the day. December 7, 1941 had destroyed 5 of America's 8 Pacific battleships at Pearl Harbor. But the real crisis emerged 6 months later during the Battle of Midway, when American carriers proved they were the new capital ships of naval warfare. Aircraft carriers now determined who controlled the Pacific, and America didn't have nearly enough of them. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By late 1942, the Navy's carrier math looked catastrophic. Essex-class fleet carriers were magnificent ships, 900 feet long, capable of launching 90 aircraft, armored to withstand punishment, and fast enough to keep pace with the entire Pacific fleet. Each one cost roughly $70 million and consumed 20 months of construction time at specialized naval shipyards. The Navy had ordered 32 Essex-class carriers, but even working at maximum capacity, American shipyards couldn't deliver them fast enough to execute the island-hopping campaign Pacific commanders were planning. Japan started the war with 10 fleet carriers. America had 7. But naval warfare in the Pacific consumed carriers at an alarming rate. The Lexington went down at Coral Sea in May 1942. Yorktown sank at Midway a month later. Wasp and Hornet were both torpedoed and lost by October. In 18 months of war, America had lost 4 fleet carriers, nearly 60% of the pre-war force. New Essex-class ships were entering service, but slowly. The first, Essex herself, wouldn't commission until December 1942. The Navy calculated they needed carriers operational now, not in 20 months when the next Essex rolled down the ways. The British had already demonstrated a partial solution. Faced with German U-boats ravaging Atlantic convoys, the Royal Navy began converting merchant ships into escort carriers. These vessels weren't glamorous. They displaced only 1/4 the tonnage of fleet carriers, operated at lower speeds, carried fewer aircraft, and lacked the armor protection that made fleet carriers survivable in major naval battles. But escort carriers could do something fleet carriers couldn't. They could be everywhere simultaneously. An escort carrier could provide air cover for convoys crossing the Atlantic, protecting merchant ships from submarine attacks. They could support amphibious landings, offering close air support for Marines storming Pacific islands, while the valuable fleet carriers remained safely offshore, launching strikes against Japanese bases. They could hunt submarines, ferry aircraft across oceans, train new pilots, and perform a dozen other tasks that didn't require a 90-plane air group and 3-inch armor plate. Most importantly, they could be built fast. The American escort carrier program began cautiously in 1941 when President Roosevelt himself directed the Navy to convert merchant ships for carrier duty. The first, USS Long Island, commissioned in June 1941, 6 months before Pearl Harbor. She was a converted cargo ship, slow, awkward, but capable of operating aircraft at sea. The Navy converted 24 more merchant hulls into Bogue-class escort carriers by mid-1942, but converting existing merchant ships created its own problems. You couldn't just bolt a flight deck onto a cargo hull and call it an aircraft carrier. Each conversion was essentially custom work. Engineers had to strengthen the hull to handle aviation fuel storage, cut holes for elevators that lifted aircraft from hangar to flight deck, install catapults for launching planes, add arresting gear for landing them, jury-rig anti-aircraft weapons wherever space allowed, and somehow retrofit electrical systems, ventilation, and crew quarters for 800 men into spaces designed for 40 merchant sailors. Every conversion took 5 to 8 months. Worse, each conversion consumed a merchant hull that could have been hauling cargo. With German submarines sinking Allied shipping faster than shipyards could replace it, using merchant hulls for carrier conversions felt like robbing Peter to pay Paul. America needed carriers and cargo ships simultaneously. Converting one to get the other just reshuffled the same limited resources. Henry Kaiser understood production in ways most naval architects didn't. The industrialist who'd built the Hoover Dam, Bonneville Dam, and Grand Coulee Dam had entered shipbuilding in 1940 when the British, already at war, desperately needed cargo ships. Kaiser had no shipbuilding experience whatsoever. That turned out to be an advantage. Unencumbered by traditional shipbuilding dogma, Kaiser looked at ship construction and saw an engineering problem similar to building a dam or paving a highway. It was about moving materials efficiently, training workers quickly, and standardizing every possible component. Traditional shipbuilding assembled vessels from the keel upward, one piece at a time. Skilled workers spent months fitting individual steel plates together, drilling holes, and driving rivets by hand. Each rivet required a team. A heater heated the rivet until it glowed red. A catcher grabbed it with tongs and positioned it in a pre-drilled hole through 2 steel plates. A bucker-up held a heavy bucking bar against the rivet tail on one side, while a riveter with a pneumatic hammer mushroomed the hot rivet head on the other side, creating a permanent mechanical joint. This process created extraordinarily strong connections, but required months of training to master and consumed massive amounts of labor hours. A medium-sized merchant ship required roughly 3 million rivets. If a team could drive 50 rivets per day, you needed 60 rivet teams working full-time for 1,000 days just to assemble the hull. Scale that across dozens of ships and you'd exhaust the entire pool of skilled riveters in America within weeks. And the military was already drafting those skilled workers for combat duty. Kaiser's innovation was brutally simple. Replace rivets with welding. Welding joined steel plates by melting their edges together, creating a fusion joint that was actually stronger than a riveted connection. A welder didn't need a 3-man team. One person with a welding rod and electrical arc could join steel plates faster than any riveting crew. Better yet, welding was easier to teach. A competent riveter required 6 months of training. Kaiser's welding schools turned out capable welders in 2 weeks. The second innovation was prefabrication. Instead of building ships entirely on the construction ways, where space was limited and workers crowded together, Kaiser built ships in pieces. Entire sections of hull, complete bulkheads, deckhouses, bow units, and stern assemblies were welded together in separate fabrication shops across the shipyard. These prefabricated modules could be built simultaneously by different crews, then lifted by enormous cranes and welded into position on the main ways. A welder working in a fabrication shop could weld overhead seams while the module sat on its side, a much easier and stronger welding position than trying to weld the same seam after installation when it might be overhead or in a cramped corner. The third breakthrough was standardization. Traditional shipbuilding treated every vessel as a custom project. Plans had to be drawn specifically for each ship, accounting for minor variations in dimensions, slightly different equipment layouts, unique modifications requested by customers. Kaiser threw out customization entirely. Every ship would use identical plans, identical components, identical everything. If a valve manufacturer supplied a specific model for Ship 1, that exact valve would appear in the exact same position on Ships 2 through 1000. This meant procurement officers could order components by the thousands from suppliers who could set up dedicated production lines. It meant workers learned one assembly sequence and repeated it identically on ship after ship. It meant mistakes made on Ship 10 could be corrected across the entire fleet by updating a single drawing. Kaiser's Liberty ship program proved these methods worked. Traditional cargo ship construction took 8 months. Kaiser cut that to 70 days, then 45 days, then an average of 42 days. In November 1942, as a publicity demonstration, Kaiser's Richmond, California shipyard assembled the Liberty ship Robert E. Peary in 4 days and 15 hours, from keel laying to launch. The ship was functional, seaworthy, and went on to serve throughout the war. But cargo ships and aircraft carriers occupied entirely different categories of engineering complexity. A Liberty ship was essentially a floating box with an engine, 5 cargo holds, a bridge, crew quarters, and propulsion machinery. An aircraft carrier, even a small escort carrier, required aviation fuel storage systems that could pump thousands of gallons of high-octane gasoline without creating explosive vapors. It needed elevators with hydraulic systems capable of lifting 14,000-pound aircraft from hangar deck to flight deck, catapult systems to accelerate aircraft to takeoff speed, arresting gear with hydraulic shock absorbers to catch aircraft landing at 70 miles per hour and stop them in 300 feet, aircraft maintenance shops, ammunition magazines, defensive weapons, radar systems, communications equipment, and flight operations spaces where controllers coordinated launches and recoveries. No one had ever mass-produced aircraft carriers. The Navy's established shipyards, places like Norfolk Naval Shipyard and New York Naval Shipyard, built carriers one at a time using traditional methods. Master shipwrights trained for decades supervised every aspect of construction. Converting Henry Kaiser's mass production philosophy to carrier construction seemed impossible. Kaiser disagreed. In mid-1942, he approached the Navy's Bureau of Ships with a proposal. Give him a basic carrier design, and he'd deliver 50 ships in 18 months using his assembly line techniques. The proposal landed on the desk of Rear Admiral Edward Cochrane, Chief of the Bureau of Ships. Cochrane's engineers reviewed Kaiser's plan and concluded it was fantasy. Aircraft carriers couldn't be mass-produced like cargo ships. The technical complexity, the precision required for flight deck construction, the integration of dozens of specialized systems, all required skilled craftsmen and extended construction time. Kaiser's proposal estimated each escort carrier could be completed in 3 months. 3 months. The Navy's existing Bogue-class escort carrier conversions were taking 6 to 8 months each, and those started with existing merchant hulls already partially constructed. Kaiser proposed building complete carriers from scratch in half that time. The Bureau of Ships rejected Kaiser's proposal. When Kaiser pressed for reconsideration, citing his Liberty ship's success, the Navy's response was polite but firm. Cargo ships and aircraft carriers weren't comparable. Rejecting the Navy's technical experts meant nothing to Kaiser. He'd faced skepticism before, from engineers who said dams couldn't be built on his accelerated schedules, from competitors who said his road paving techniques would fail. His response was consistent: go over their heads. In August 1942, Kaiser secured a meeting with President Roosevelt's advisors. Roosevelt, a former Assistant Secretary of the Navy, understood naval warfare intimately. He also understood production bottlenecks. The President was already frustrated with the Navy's slow carrier construction pace. When Kaiser explained he could deliver 50 small carriers before the Navy's shipyards could build 5 fleet carriers, Roosevelt overruled his own admirals. The President personally directed the Navy to award Kaiser a contract for 50 escort carriers, designated the Casablanca class. The admirals weren't happy. They'd been professionally humiliated by a civilian industrialist with no naval architecture background. Worse, they were convinced Kaiser's carriers would be death traps. Rushed construction using inexperienced workers and untested mass production methods would produce inferior ships that would crack apart in Pacific storms or explode when Japanese bombs found poorly protected aviation fuel tanks. The Navy brass privately called them Kaiser's coffins, a nickname that would stick throughout the war. But Roosevelt's word was final. In June 1942, Kaiser's Vancouver shipyard on the Columbia River received the formal contract, 50 escort carriers. Delivery schedule beginning April 1943. The clock started ticking. The Vancouver yard had been constructed specifically for Liberty ship production just months earlier. Now Kaiser's engineers had to completely retool it for carrier construction, while simultaneously completing Liberty ships already in progress. The yard featured 12 building ways where ship keels were laid, plus an enormous 3,000-foot outfitting dock where completed hulls received final equipment installation before commissioning. Kaiser's team started with the Navy's basic specifications. The Casablanca class would measure 511 feet long, with a 56-foot beam. Displacement would be 7,800 tons empty, over 11,000 tons fully loaded with fuel, aircraft, ammunition, and crew. The flight deck would extend 512 feet, providing just enough length for aircraft operations. Power would come from uniflow reciprocating steam engines, not the turbines used on fleet carriers, because gear-cutting bottlenecks made turbines unavailable. The reciprocating engines were slower but available immediately from existing suppliers. Each carrier would accommodate 28 aircraft in peacetime configuration, though wartime necessity often pushed that number higher. The air group typically included 16 fighter aircraft and 12 torpedo bombers. For self-defense, each carrier mounted one 5-inch 38 caliber gun at the stern, plus numerous 20mm and 40mm anti-aircraft guns. Crew complement was established at 860 officers and enlisted men. The real engineering challenge wasn't the specifications. It was translating those specifications into components that could be prefabricated, standardized, and assembled by workers who'd never built a carrier before. Kaiser's chief naval architect, a man named Stephen Bechtel, led the design translation effort. Bechtel had worked with Kaiser on the Hoover Dam and understood the industrialists' production philosophy intimately. Bechtel's first decision involved the hull structure itself. Traditional naval architecture built carriers with complex double-bottom hulls, multiple watertight compartments, and elaborate damage control systems. Every connection point required custom fitting by skilled shipfitters. Bechtel simplified ruthlessly. The Casablanca hull would use a single bottom design with fewer but larger watertight compartments. This reduced the number of unique structural components by 60%. The flight deck presented the next challenge. A carrier's flight deck must be absolutely flat across its entire length. Any irregularity, even an inch-high bump, could catch an aircraft's landing gear and cause a crash. Traditional carrier construction achieved this flatness through patient hand-fitting by master craftsmen who spent weeks shimming, grinding, and adjusting deck plates until perfection was reached. Bechtel's solution involved prefabricating the entire flight deck in 6-foot-wide longitudinal sections. Each section was built in a fabrication shop, where workers could use precision leveling equipment and weld the deck plates while the section lay flat on a factory floor. Once fabricated to exact specifications, these deck sections were lifted by crane and bolted into position atop the carrier's hull structure. The bolt-together assembly method meant deck sections could be manufactured simultaneously at different locations, then delivered to the ways just in time for installation. Hangar deck systems required similar innovation. The hangar, located one deck below the flight deck, provided enclosed space for aircraft maintenance and storage. 2 elevators moved aircraft between hangar and flight deck. Traditional carriers used complex hydraulic elevator systems custom-built for each ship. Bechtel standardized every elevator component: motors, hydraulic pumps, cables, platform dimensions, everything identical across all 50 ships. aviation fuel systems terrified everyone involved. High-octane aviation gasoline was extraordinarily volatile. Improper storage or fuel line routing could turn a carrier into a floating bomb if combat damage ruptured tanks or pipes. The Navy had decades of experience designing fuel systems with multiple redundant safeguards, isolated tank compartments, and CO2 fire suppression systems. Bechtel had to replicate that safety in a mass production environment using workers who'd never even seen an aircraft carrier before, let alone designed complex fuel systems. The solution involved creating a completely modular fuel system. Fuel tanks were standardized units, prefabricated complete with mounting brackets, fill pipes, vent systems, and damage control valves. These units could be built and pressure tested in a dedicated facility, then delivered to the ship as complete assemblies. Fuel lines used a color-coding system: red pipes for aviation fuel, green for diesel, blue for fresh water, black for waste. Workers couldn't possibly install a fuel line in the wrong location because the colored pipes physically wouldn't fit wrong-colored connection points. Kaiser's welding revolution formed the foundation of everything. But welding introduced its own technical challenges that nearly derailed the entire program before it began. Traditional riveting created mechanical joints. Two steel plates overlapped slightly, holes were drilled through both, and a rivet was driven through to hold them together. The rivet expanded when hammered, creating a tight mechanical lock. If the joint failed, it failed gradually. Rivets would loosen, start leaking, give warning signs that maintenance was needed. Riveted ships could take tremendous punishment and still limp home because even if some rivets failed, thousands of others kept the structure intact. Welding worked fundamentally differently. Instead of mechanical connections, welding created metallurgical bonds. The edges of two steel plates were heated until molten, fused together, and allowed to cool into a single piece of metal. When done correctly, a welded joint was stronger than the base metal itself. The problem appeared when welding was done incorrectly or when unforeseen stresses affected welded structures. The issue was called brittle fracture, and nobody fully understood it in 1942. Under certain conditions, welded steel could crack catastrophically. Unlike riveted structures that failed gradually, a crack in a welded ship could propagate rapidly, racing through welded seams like a zipper opening. In cold water, under heavy loads, or when weld quality was poor, cracks could split an entire ship in two within minutes. The problem first appeared in Liberty ships during 1943. Several Liberty ships sailing through North Atlantic winter waters literally broke apart. One moment the ship was intact, steaming through rough seas. The next moment, the hull cracked completely across the midships section, and both halves sank within minutes. The SS Schenectady split in two while moored in calm water in Portland Harbor in January 1943. The ship was simply floating at the dock when a crack suddenly appeared and propagated around the entire hull. Within hours, the ship had broken completely apart, its bow and stern sections resting on the harbor bottom. Engineers investigated frantically. They discovered that certain welding techniques, particularly when performed by inexperienced welders in cold weather, created microscopic defects in the weld metal. These defects acted as stress concentrators. When the ship flexed in heavy seas or encountered very cold water temperatures that made steel more brittle, cracks initiated at these defect sites and propagated catastrophically through continuous welded seams. The solution required multiple changes. First, steel chemistry was modified to add elements that reduced brittleness. Second, critical structural areas received crack arrestor plates, riveted sections deliberately inserted into otherwise welded structures. If a crack started propagating, it would reach a riveted section and stop because cracks couldn't jump across mechanical joints the way they could race through welded seams. Third, welding inspection became far more rigorous. Fourth, welders received better training in proper technique, particularly regarding the preheat temperatures required before welding in cold conditions. But in mid-1942, when Kaiser's Vancouver yard was setting up for Escort carrier production, These solutions hadn't been discovered yet. Kaiser's team was betting the entire program on welding techniques that could potentially kill everyone aboard if the ships cracked open in the middle of the Pacific Ocean. The Navy's concerns about Kaiser's coffins suddenly seemed less like prejudice and more like legitimate engineering caution. Kaiser responded by implementing the most comprehensive welding quality control system in American shipbuilding. Every welder was tested and certified before touching a carrier hull. Welding inspectors examined every inch of every seam using X-ray equipment borrowed from medical facilities. Critical structural welds were ground down and re-welded if inspections showed any defects. The extra inspection time added cost and complexity, but it ensured that escort carriers leaving Vancouver were welded properly. The actual construction process that Kaiser's team developed represented a complete reimagining of how warships could be built. Walk through the Vancouver yard in early 1943 and you'd see something that looked more like an automobile factory than a traditional shipyard. Building Way 3, where Hull 1092 took shape, was actually the final assembly area. The real construction happened in dozens of fabrication shops scattered across the 70-acre yard. Shop 12 built bow sections. Shop 8 fabricated stern assemblies. Shop 15 specialized in deckhouses. Shop 22 produced the massive steel frames that supported the flight deck. Each shop operated like an independent factory, churning out identical components for multiple carriers simultaneously. In Shop 12, workers assembled the bow using massive steel frames arranged in a jig that held everything in perfect alignment. The frames were prefabricated elsewhere, delivered to Shop 12, positioned in the jig, and welded together while the entire assembly sat on its side. Welders could walk around the structure, accessing every joint easily. Once the bow section was complete, hydraulic jacks rotated it upright, and a 400-ton crane lifted the entire 50-foot-tall, 120-foot-long bow section and transported it to the building ways. The same process happened simultaneously in every fabrication shop. While Crew A welded bow section for Carrier 15, Crew B in the same shop was starting bow section for Carrier 16. Stern sections, midship sections, deck houses, flight deck supports all moved through their respective shops in assembly line fashion. On the building ways, a different choreography unfolded. The keel plate, essentially a massive steel foundation beam running the ship's entire length, was laid first. Then prefabricated bottom sections were lifted into position by cranes and welded to the keel. These sections included the double bottom compartments where ballast water and fuel oil would be stored. As bottom sections took shape, workers inside the hull installed piping, electrical conduits, and equipment mounts while the structure was still easily accessible. Side sections came next. These vertical steel wall sections, complete with portholes already cut and reinforced, were lifted and welded into position. Each side section stood 30 feet tall and weighed 15 tons. Crane operators positioned them within 1 inch of true, using guidance from surveyors with optical instruments. Once aligned, welders secured them permanently. The process moved from stern to bow, 1 section every 8 hours. As the hull took shape, the stern section arrived from its fabrication shop. This massive assembly included the steering gear, propeller shaft housings, and the mounting bracket for the single 5-inch gun. The entire stern, prefabricated as one unit weighing over 200 tons, was lifted by the yard's largest crane and lowered into position. Bolt holes aligned because tolerances throughout the fabrication process kept everything within 1/8 inch specifications. Welders worked around the clock to fuse the stern section to the main hull. 3 days after the keel plate was positioned, the basic hull structure was complete. Now the ship looked recognizable as a carrier hull, 511 feet of steel sitting on the ways. But it was still just an empty shell. Transforming it into a functional warship required installing thousands of components while simultaneously maintaining the aggressive schedule. This is where Kaiser's just-in-time delivery system proved crucial. Traditional shipbuilding stockpiled components months in advance. Kaiser did the opposite. Components arrived at the building ways exactly when needed, not hours before or after. The island superstructure, the small tower on the flight deck where ship's officers controlled operations, arrived from its fabrication shop the same day. Workers were ready to install it. It was lifted into position, bolted down, and welded secure within 12 hours. The flight deck came next, delivered in 6 massive prefabricated sections. Each section measured 80 feet long by 65 feet wide and weighed 40 tons. Crane operators, working in coordinated teams, lifted these sections simultaneously and lowered them onto the support structure. The sections had bolt holes pre-drilled at the factory. Workers simply inserted bolts, torqued them to specification, and welded doubler plates over critical joints. The entire flight deck installation took 18 hours. Elevator systems arrived as complete assemblies. The elevator platform, its guide rails, hydraulic rams, motors, control systems, safety interlocks, everything was pre-assembled and tested at a dedicated elevator facility. This complete unit was lowered through the flight deck opening, positioned, and connected to ship's power and control systems. Testing began immediately. If the elevator could lift a 14,000-pound test weight from hangar to flight deck and back 20 times without malfunction, it passed inspection. Aviation fuel systems, the most dangerous components, received dedicated installation crews who did nothing else. These specialists understood the color-coded pipe system intimately. They connected prefabricated fuel tank modules to prefabricated distribution piping using standardized fittings that eliminated any possibility of connecting incompatible components. Every connection was pressure tested to 3 times normal operating pressure. Any leak, any defect, meant that entire section was cut out and replaced. Electrical systems presented their own complexity challenge. An Escort carrier required over 40 miles of electrical cable connecting generators, lighting systems, radar equipment, radio gear, weapons, fire control computers, and hundreds of other electrical loads. Kaiser's team pre-assembled cable bundles on mock-up frames that replicated the ship's internal structure. These bundles arrived at the ship as organized groups of cables, already secured to supporting cable trays, with connectors pre-installed and labeled. Electricians simply positioned the bundle, secured it with mounting clamps, and tested continuity. By day 7, workers were installing the smaller components: anti-aircraft guns, radar antennas, life raft racks, crew berthing spaces, galley equipment, medical facilities. The pace never slackened. Every 8-hour shift had specific completion targets. Fall behind, and the entire schedule cascaded into chaos. The most remarkable aspect was workforce composition. In 1943, Kaiser's Vancouver yard employed over 38,000 workers. Roughly 30% were women, many of whom had never worked outside their homes before the war. Another significant percentage were African Americans recruited from across the country during a period when defense industries typically excluded them. Wounded veterans, physically disabled individuals, retirees, anyone willing to learn and work found employment at Kaiser's yards. These workers weren't master craftsmen. They were farmers, housewives, store clerks, teenagers, and retirees given 2 weeks of training and assigned to repetitive tasks they could master quickly. The woman welding a seam in a deckhouse might have been teaching elementary school 6 months earlier. The crane operator positioning a 50-ton stern section might have been working as a bank teller in 1941. The entire system depended on breaking complex shipbuilding into simple, repeatable tasks that could be performed by anyone willing to learn. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By November 12, 1942, exactly 72 hours after the keel plate dropped into position, Hull 1092 was ready for launch. The ship wasn't complete. It still needed weeks of work at the outfitting dock, but the basic structure was sound enough to float. This was the critical moment. If the ship didn't float properly, if welds leaked catastrophically, if the structure cracked under its own weight when it hit the water, the entire program would be revealed as the disaster the Navy had predicted. Eleanor Roosevelt, the First Lady, travelled to Vancouver to christen the ship. Originally designated Amir and intended for transfer to the Royal Navy under Lend-Lease, plans had changed. The ship would serve in the U.S. Navy as USS Alazon Bay, later renamed Casablanca after the naval battle that had secured Allied control of North Africa. On a cold, rainy November morning, Mrs. Roosevelt stood at the bow and smashed a champagne bottle against the hull. Workers knocked away the wooden support blocks, holding the ship on the ways. Slowly, then faster, the 8,000-ton hull slid down the greased launching ways and crashed into the Columbia River, sending spray 50 feet into the air. The ship floated, perfectly level, no obvious leaks. Tugs maneuvered the hull to the outfitting dock, where workers would spend the next 60 days installing equipment too delicate to install before launch, testing systems, training the crew, and preparing the carrier for sea trials. But the 72-hour assembly time had been proven. It wasn't propaganda. It wasn't a fluke. It was repeatable. Kaiser immediately ramped up production. By January 1943, all 12 building ways were simultaneously constructing escort carriers. Every 3 days, another hull launched. The fabrication shops ran 3 shifts around the clock. Components flowed from shops to building ways in a continuous stream. The outfitting dock accommodated 20 carriers simultaneously, each at a different stage of completion. The Navy sent inspection teams who couldn't find obvious flaws but remained skeptical. These ships were being built too fast. Something had to be wrong. Inspectors crawled through bilges looking for defective welds. They X-rayed structural joints. They tested every system repeatedly. The Casablanca-class carriers passed every inspection. Quality metrics showed these mass-produced carriers actually had lower defect rates than traditionally built escort carriers from other yards. Why? Because standardization eliminated the variability that caused most defects. When every ship used identical components installed in identical locations using identical procedures, workers became experts at their specific tasks. The 100th time a worker welded a specific joint, they did it better than the first time. The 1,000th time a crane operator positioned a deck section, they achieved better precision than the initial attempt. Repetition bred expertise even among workers with minimal initial training. By April 5, 1943, exactly 5 months after construction began, USS Casablanca commissioned into active service. She wasn't pretty. The ship rolled heavily in rough seas due to its relatively narrow beam and tall superstructure. The single-bottom hull design made her more vulnerable to torpedo damage than fleet carriers with elaborate underwater protection systems. The Uniflow reciprocating engines limited top speed to 20 knots, barely fast enough to keep pace with convoy operations. Crew spaces were cramped. Ventilation was inadequate in tropical heat. The ship earned nicknames that reflected these limitations. Kaiser's coffins, combustible, vulnerable, expendable, baby flat-tops, jeep carriers. But she worked. On July 23, 1943, Casablanca embarked her first air group for training operations in the Strait of Juan de Fuca. For the next year, she operated as a training carrier, qualifying pilots for combat and providing pre-commissioning training for crews of other Casablanca-class carriers being completed at Vancouver. She gathered operational data, testing how escort carriers performed during extended sea time. The Navy used this information to refine subsequent ships. Meanwhile, the production line at Vancouver never stopped. Between April 5, 1943 and June 8, 1944, Kaiser's Vancouver yard launched 50 Casablanca-class escort carriers, 50, in 14 months, nearly 1 carrier per week. No shipyard in history had produced capital warships at this rate. The final production numbers revealed the magnitude of Kaiser's achievement. Average construction time from keel laying to launch dropped to 71 days for the entire class. Average time from keel laying to commissioning, including outfitting and sea trials, averaged 3 months and 10 days. Compare those numbers to any other carrier program in history. Essex-class fleet carriers, 20 months. British Illustrious-class carriers, 36 months. Japanese Shokaku-class carriers, 32 months. Even the Bogue-class escort carrier conversions that preceded the Casablanca class took 6 to 8 months each, and those started with existing merchant hulls. Kaiser had compressed carrier construction time by a factor of 5 compared to conversions and by a factor of 7 compared to fleet carrier construction. The strategic impact was immediate and profound. By late 1943, escort carriers appeared across every theatre of the Pacific War. They supported amphibious landings at Tarawa, providing close air support for Marines storming the beaches. They hunted Japanese submarines in the vast expanses between major island groups. They ferried replacement aircraft from Pearl Harbor to forward bases, traveling routes too dangerous for unarmed cargo ships. They trained replacement pilots, allowing fleet carriers to focus exclusively on combat operations. In the Atlantic, Casablanca-class carriers formed the core of hunter-killer groups that systematically destroyed German U-boats. Operating with destroyer escorts, these carriers used aircraft equipped with radar and depth charges to locate and attack submarines. Between 1943 and 1945, escort carriers and their accompanying destroyer escorts sank 53 German submarines, effectively ending the U-boat threat to Allied convoys. The most dramatic test came during the Battle off Samar on October 25, 1944. 6 Casablanca-class carriers of Task Unit Taffy 3 found themselves facing a Japanese battle fleet, including the battleship Yamato, the largest battleship ever constructed, plus 3 other battleships, 6 heavy cruisers, and numerous destroyers. This was no fair fight. Yamato displaced 72,000 tons and mounted 18-inch main guns that could hit targets 26 miles away. A single salvo from Yamato could vaporize an escort carrier. Admiral Clifton Sprague, commanding Taffy 3, faced an impossible situation. His 6 escort carriers, escorted by 3 destroyers and 4 destroyer escorts, represented the only force between the Japanese fleet and the undefended American amphibious forces landing at Leyte Gulf. If the Japanese broke through, they would massacre the transport ships and potentially derail the entire Philippines campaign. Sprague ordered his carriers to launch every available aircraft, even those armed only with depth charges intended for submarine hunting. He ordered his destroyers and destroyer escorts to attack the Japanese battleships with torpedoes, a suicidal mission given the overwhelming firepower disparity. Then he ordered the carriers to run. At their maximum speed of 18 knots, they couldn't outrun Japanese battleships capable of 27 knots, but every minute of delay bought time for American reinforcements to arrive. For 2.5 hours, Taffy 3 fought the most one-sided naval battle in American history. Japanese battleship shells straddled the fleeing carriers, sending up towering water columns. USS Gambier Bay, one of the Casablanca-class carriers, took multiple hits and sank. Streetlow, another Casablanca-class carrier, survived the surface engagement but was hit by a kamikaze aircraft and exploded. 2 destroyers and 1 destroyer escort were sunk, but Taffy 3 won. The combined attacks by aircraft, destroyers, and destroyer escorts convinced Japanese Admiral Kurita that he was facing a much larger American force than actually existed. Concerned about ammunition expenditure and fearing additional American reinforcements, Kurita withdrew. The Japanese had lost 3 heavy cruisers sunk and numerous ships damaged. More importantly, they'd failed to reach the amphibious landing forces at Leyte Gulf. The Philippines invasion continued. The battle vindicated every aspect of Kaiser's mass production philosophy. Yes, the escort carriers were vulnerable. Gambier Bay and Streetlow were sunk, proving the Kaiser's coffin's nickname had some basis in reality. But 4 Casablanca-class carriers survived a battle they had no business winning. Their aircraft, despite being armed for anti-submarine work rather than surface attack, managed to sink cruisers and damage battleships. Their crews performed magnificently under impossible conditions. Most tellingly, none of the carriers suffered structural failures, weld cracks, or the catastrophic brittleness problems the Navy had feared. Casablanca-class carriers continued serving through the end of the war. They supported every major amphibious operation from late 1943 through 1945: Tarawa, Saipan, Guam, Palau, Peleliu, Philippines, Iwo Jima, Okinawa. Every landing had escort carriers offshore, providing close air support. Of the 50 Casablanca-class carriers completed, 5 were lost to enemy action during the war. Liscombe Bay, torpedoed by a Japanese submarine in November 1943, Gambia Bay and Street, Low at the Battle of Samar. Omani Bay and Bismarck Sea, both destroyed by kamikaze attacks in 1945. The 45 surviving carriers transitioned to various post-war roles. Some became aircraft transport ships, ferrying planes between bases. Others participated in Operation Magic Carpet, bringing American servicemen home from overseas bases. Several were converted to escort helicopter carriers during the Korean War, but by the mid-1950s, all had been decommissioned and sold for scrap. None survive today. The most numerous class of aircraft carriers ever built, 50 ships launched in just over a year, has completely disappeared except for photographs and memories. What does survive is the production methodology that made them possible. Modern shipbuilding, whether military or commercial, still uses Kaiser's fundamental insights. Modular construction, where ships are built in sections that are assembled on the ways. Extensive prefabrication in dedicated fabrication shops. Just-in-time delivery systems that minimize inventory costs. Standardization of components across multiple ships. Welding instead of riveting. All of these practices trace directly back to Henry Kaiser's Vancouver shipyard in 1943. The escort carrier program proved something profound about industrial warfare. In total war, production capacity becomes as important as military strategy. Germany and Japan possessed superior military technology in many areas at the start of World War II. German U-boats were more sophisticated than American submarines. Japanese Zero fighters were more maneuverable than American Wildcats. German Tiger tanks were better armored than American Shermans. But superior technology didn't matter when America could produce 5 ships for every 1 Germany built, 3 aircraft for every 1 Japan manufactured, and 10 tanks for every German tank destroyed. Kaiser's escort carriers embodied this production advantage. Were they the best carriers in the world? No. Fleet carriers were faster, better armored, carried more aircraft. Even other escort carrier designs had advantages. The Sangamon-class conversions from fleet oilers were larger, faster, and more survivable than Casablanca-class ships. But fleet carriers took 20 months to build, and Sangamon conversions still required 6 months each. When you needed 50 carriers to simultaneously support operations across 2 oceans, only Kaiser's 3-month construction time made that possible. The human story matters too. Those 38,000 workers at Vancouver weren't military personnel following orders. They were civilians choosing to work 12-hour shifts, 6 days a week, in dangerous conditions for the duration. Welding is hazardous. Fall from a scaffold, and you're dead. Breathe welding fumes for years, and your lungs deteriorate. Work near molten metal and burns become routine. The women who became Wendy the Welder, working jobs traditionally reserved for men, did so knowing that their sons, husbands, and brothers were fighting in the Pacific. Every carrier they completed put more American aircraft over Japanese positions, protecting ground troops and potentially saving lives. The Vancouver workforce came from everywhere. Thousands relocated from other states, creating housing shortages that eventually required Kaiser to build an entire temporary city, Vanport, to accommodate workers. The community included unprecedented racial diversity for 1940s America. African Americans, Japanese Americans, Latinos, Native Americans, whites, all working side by side in shipyards, where the only thing that mattered was whether you could do the job. This wasn't idealistic integration, it was pragmatic necessity. America needed ships faster than prejudice could provide them. By war's end, American shipyards had produced 151 escort carriers total across multiple classes. Casablanca-class ships represented exactly 1/3 of that total, 50 ships from a single yard in 14 months. Those 50 carriers operated collectively for the equivalent of thousands of ship years, carrying over 1 million flight operations, launching aircraft that sank submarines, supported amphibious operations, and hunted Japanese naval forces across the Pacific. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.